Hi, and welcome to the LISA Symposium. My name is Victoria DeCoon, and I'm from Miami, Florida, attending Florida International University as an undergraduate, majoring in physics with a minor in astronomy. This summer, I've worked with Jillian Bellovary in detecting merging black holes in dwarf galaxies. Dwarf galaxies are the most abundant type of galaxy in the universe. They are generally difficult to detect due to their low luminosity, low mass, and small size. Dwarf galaxies have black holes in them. There are three main types of dwarf galaxies, including elliptical, spheroidal, and irregular. Elliptical dwarf galaxies are elliptical in shape, contain very little or no gas, and have no evidence of recent star formation. Spheroidal dwarf galaxies tend to be much smaller than ellipticals, and as the name suggests, more spherical. Irregular dwarf galaxies contain substantial amounts of gas and dust with clear evidence for ongoing star formation. This image displays an example of an irregular dwarf galaxy, NGC 5477, from the Messier 101 group, showing evidence of star formation. These images show evidence of black holes in dwarf galaxies. On the left is Hanese 210 from Raines 2011, with the black hole mass calculated to be about 1 million solar masses. On the right is RGG 118 from Baldessari 2017, with the black hole mass calculated to be about 50,000 solar masses. This shows us that black holes indeed exist in dwarf galaxies, and there could be potentially many more that we cannot see because they are not active. To predict gravitational wave signals from merging black holes in dwarf galaxies, we use the Changa code to create cosmological smooth particle hydrodynamical simulations. We have two sets of high-resolution simulations which include dwarf galaxies with black holes. One suite, known as the Marvelous Dwarfs, consists of 4 volumes filled with dwarf galaxies. For the other suite, known as the DC Justice League, each simulation consists of one large Milky Way-like galaxy surrounded by many dwarf galaxies, some of which host black holes as well. This set of simulations is the highest resolution set of simulations which follow black holes and dwarf galaxies from the epoch of black hole formation to the present day. Black holes form self-consistently in our simulations from gas particles which are dense, collapsing, and have low metallicity and low molecular hydrogen fractions. These criteria most closely mimic the direct collapse model of black hole formation, and the black hole seed mass is 50,000 solar masses. The black hole particles experience dynamical friction via a subgrid model as described by Trummel 2015. Black hole particles merge when they become close together in space, about 350 kiloparsecs, and have low relative velocities to ensure they are not whooshing past each other, but are approximately gravitationally bound. 350 parsecs is not close if you're a black hole. There's a lot of physics that happens to get the black holes from this point to coalescence, but the simulation's limited resolution can't capture it. This is where my research comes in, where I am able to account for the physics involved. Taken from Bellovary 2019, this plot shows 11 different binary black hole merger events in dwarf galaxies from the cosmological simulations mentioned earlier. On the y-axis is redshift, and x-axis is total mass and solar masses. Black points show these merger events as a function of redshift and the combined black hole mass. Near each black point is the mass ratio of each merger. Rainbow contours in smaller numbers represent the signal-to-noise ratio with which LISA will detect such mergers. Red is most detectable, with blue being the least detectable. I have used this information to calculate delay times for each merger. I am researching merging black holes in dwarf galaxies, and to do this, I have been using Python with Pinbody to collect data from cosmological simulations, such as finding the number of black holes and their positions within a dwarf galaxy, determining star and gas mass, creating density profiles, and calculating the velocity dispersion. Now, the goal is to discover how long it takes for black holes to merge in dwarf galaxies, because if they do merge, LISA will detect them. Since dwarf galaxies are very common, their black hole mergers might also be common. The obstacles are not knowing how often black holes merge, nor how many black holes are within a dwarf galaxy. The solution is having cosmological simulations where black holes form and merge, and then creating and using models to calculate delay time to do a better job of estimating reality. Delay time depends on the properties of galaxies, and I have measured these properties during my research. I created my own gravitational wave strain plot, which compares 11 different binary black holes that merge inside dwarf galaxies from these simulations. The y-axis characteristic strain is essentially how much the gravitational wave distorts spacetime and how strong the wiggle is. The x-axis is the frequency of the gravitational waves. This plot showcases the in-spiral, where black holes are getting closer together until the merger, and finally the ring down, where space-time flattens out and adjusts to distortion. The dashed blue line tells us where LISA will be able to detect the gravitational waves, and the orange dashed line shows us the galactic background. But before we see some results, let's spend some time understanding large-scale delay, dynamical friction, and hardening. In these images that I drew, the red is a galaxy surrounding the black hole, and the black hole is depicted by the black filled circles. Large-scale delay, also known as large-scale orbital decay, has the largest orbit and is a gradual decrease of the distance between two orbiting black holes at their closest approach over many orbital periods. These orbits do not decay without some friction-like mechanism which transfers energy from the orbital motion, which in this case would be due to dynamical friction. During the large-scale delay stage, the galaxies and the black holes are still separated. Dynamical friction, sometimes called gravitational drag, has a medium-sized orbit and is the loss of momentum and kinetic energy of moving bodies through gravitational interactions with surrounding matter in space. This is important during the middle of the in-spiral process and not efficient when black holes are far apart. During the dynamical friction stage, the galaxies merge, but the black holes are still orbiting each other. Hardening is when this smaller orbit shrinks due to gravitational waves and occurs at the end of the in-spiral right before the merger. At this stage, the black holes form a binary and are very close together. Gravitational waves only release a lot of energy if the black holes are really close together. After this stage, coalescence occurs where black holes merge into one black hole. While previous simulations are great, they ignore all this important physics I'm showing here, and this is why I consider my research very important to understanding and including these processes. In order to produce results, there's a few things I must do first, such as identifying masses of black holes, their mass ratios, their halos, and their redshifts. Then I move on to calculate slopes of stellar density profiles, distances between black holes, stellar velocity dispersions, until finally calculating the delay times of the black hole mergers in dwarf galaxies. Displayed is a plot of the stellar density profile of the galaxies hosting the black holes, with the slope included for merger at redshift equals 1.75. The y-axis is the density, or how tightly packed the galaxy is or isn't, and the x-axis is the radius, where left is center and right is outwards towards the edge of the galaxy. A greater, steeper slope means it is more dense, and the black holes will merge easier with a shorter delay time. A flatter slope means it is less dense with a more erratic path for the black hole to get to the center, and is not likely to stay in the center. The more dense the galaxy is, the more slowing of movement towards the center is. This means that the black holes in a denser galaxy are more likely to find each other in the center and stay there. Though some dwarf galaxies are more likely to be less dense, the stellar density profile shown proves to be promising with a decently steep slope. Next, we calculate the delay time. Coalescence time is the age of the universe when black holes merge plus the delay timescale. The delay timescale is how long it takes for where they are in the simulation to actually touch. For example, if the universe was 4 billion years old and the delay timescale is 1 billion years, coalescence time would be 1 plus 4, so 5 billion years. Now, what sums up to become the delay timescale is large-scale delay, dynamical friction, and hardening due to gravitational radiation, which we just explained. Our universe is 13.7 billion years old, and the coalescence time shown is 3.81 billion years, meaning it is this age when the black holes merge. They get closer together, or essentially find each other, 7.5 million years before that. Thus, we and LISA can observe this merger because it happens 3.81 billion years after the Big Bang. Slope and delay time for merger at redshift equals 9.42. For this one, we have a nice steep slope, but unfortunately, due to the coalescence time, we won't be able to observe this merger. The hardening time is very long, preventing them from merging anytime soon. Slope and delay time for merger at redshift equals 3.79. Again, we have a nice steep slope, and the good news is that this coalescence time informs us that we will be able to observe this merger. Slope and delay time for merger at redshift equals 4.60. Slope is not as steep as the others, but the coalescence time informs us that we will be able to observe this merger. Slope and delay time for merger at redshift equals 0.392. This shows that we will be able to observe this merger because it's not too long ago or that far away. This means this could be a really high signal event. Out of the 11 mergers, we calculated 5 delay times, and the other 6 are unresolved. Out of the 5 calculated, only 4 will merge within a Hubble time and can be observed by LISA. The plot on the right is the same one shown earlier, except now I've identified the different mergers. Purple dots are the observable mergers, pink is the unobservable mergers, and the black dots are unresolved. Future work includes calculating the delay times a different way using the Kelly 2017 model and repeating these calculations for the Romulus simulation, which will allow us to calculate global merger rates. This concludes my presentation on detecting merging black holes in dwarf galaxies. Thank you for your attention.